welcome. We continue with the second lecture in the course Computer Science in Climate and Ocean Research, and the topic of this lecture is the modularization of climate models. The aim of modularization is to obtain flexibility in the code and flexibility with respect to different models and also with respect to different time integrators. So to motivate this, I will first of all present a second model that we will also treat in the exercises, and then I will also describe a different time integrator. And then we come to the modularization, and both in a structural programming setting and in an object-oriented setting. So starting with the second model, or as repetition, starting with a mathematical formulation of a climate model, again, as in the first lecture, we are treating initial value problems for systems of ordinary differential equations. So we have a differential equation where the unknown function, the blue one, is appearing in the equation, but there's also the derivative, the red one, appearing in this equation. So we have both in it, and this is the main point for a differential equation, the main difficulty. Here we see the definition of the derivative, and example always global mean temperature would be the simplest example, and it's an ordinary differential equation because we have just one derivative. Usually we will have a system of differential equations where the vector, where y, the function, is a vector, and also the model function f then is a vector. And additionally we need an initial value denoted here by y0 at a given initial time instant. So these two equations together, the differential equation together with the initial value, this forms the initial value problem. And last time we had already one example, the zero-dimensional energy balance model, and it was like this. So here we have, it's a little bit, now here I wrote it in the way that it's also on the exercise, so I included the constants. So we have here the solar constant, we have some a coupling constant C here, and then we have the albedo, and we have here the emissivity, which is a quantity that describes the effect of the greenhouse effect, and then we have the Stefan-Boltzmann constant here, and here we have the power of 4 of the unknown function y, which is a temperature, and here we have the time derivative. So this is the first model. It has one equation, so y is one-dimensional, so we have one ordinary differential equation together with an initial value. The second example is a system of equations. It's a predator-prey model. So we take it as the next, a little bit more complicated example for a different model, and it models an ecosystem with two species, the prey and the predator. So it was developed for population of animals in, some people say it's coming from fish population in the Mediterranean Sea. Some also you will find that it's coming from other population, ecosystem with two populations. And it's connected with the names Lotka and Volterra. So for us, what's important, we have now two equations. We have also two functions, x and y. And here I omitted already the argument t, so this is the abbreviated description of a system of ordinary differential equation. So that's what's usually done in mathematics, that the argument t is omitted to keep it more compact in the notation. And you can see here it's a coupled system, so x dot depends on x, but also on y. And the other way around, also y depends also, or y dot depends on y and x. And we have here some parameters, alpha, beta, gamma, delta, lambda and mu. So in the most simple form, the lambda and mu terms are omitted, but then we have still a coupling between the two components. We have a bilinear function, x times y, is appearing in both equations. And the modeling is like this. If you consider, let's say you have a beta also equal 0, then you would have here x dot equals alpha times x, and since all parameters are assumed to be positive, this would give then an exponential growth of the prey. So if there is no predator present, then the prey will grow, or the population size of the prey will grow exponentially. And if there is a predator present, then this growth is decreased, because we have here a negative sign, and it can be that the prey also dies out. And for the predator, it's the other way around. If there is no prey, then you can see there is a negative constant here, so the predator will die out. But if there is some something to eat, then here there will be, the predator can survive. And usually you get some periodic behavior, as I will show in the next slides. This additional terms for social interaction lead to some, even if there is no predator here and the population of the prey grows, then there will be also a diminishing term here, because there is then social interaction, and the idea is if there are too many, that the species or the population is too big, then the prey population will decrease again, because there is social interaction and competition between or inside the species, even without a predator, and the same is for the second equation. So there you can also compute easily periodic, not easy periodic solutions, but stationary points at 0, 0, and at these 2 points if there is no social interaction inside. So this is a model which is somehow flexible. You can also assume that the constants are time dependent, then it becomes more and more complicated, but in the first case we just consider this example with parameters alpha, beta, gamma, delta greater than 0, and we want to see what is happening. This is a typical example without the quadratic terms, so without these social interaction terms. Then you get a periodic behavior. If we plot here x and y versus t, you see that they are here denoted by y1 and y2 for x and y. You can see that there's a periodic behavior of both species, but a little bit shifted. Of course, if the one species goes down, the other will grow. For example, if there's very little population or small population of predator, then the prey will grow, but then the predator will population will also grow, which diminishes the prey population. And this can be easily seen in this picture. And another typical picture that's always shown, or shown in many cases, is a y versus x, which for a periodic solution gives some closed curve. And you can see here, this is already computed with a numerical algorithm. You can see here that's not really smooth. That depends on the time step, of course, of the numerical solver I use. So it's not easy to write down, or it's not possible in general to write down an explicit solution, so x as a function of t. So we need numerical methods. Without quadratic terms, so we have a periodic solution. If we include the quadratic terms, then it of course depends on the parameters, but there could be happening something like this, that the solution approaches a stationary point here, so like a spiral. So there's no periodic solution in general for if lambda and mu are not equal 0. Okay, so this is a nice example because you can plot it. It's not that difficult to simulate, it takes not much time, but still you can play with parameters and see different behavior. Okay, coming to different time integrators. Again, a repetition where we have the discretization of ordinary differential equations. So we split up the time interval from t0 to t in equidistant time slices with delta t as a length of each slice. Then we approximate the derivative, and we start, in the simplest case, we end up with the explicit Euler method like this. And we also know, or the mathematicians know, the numerical mathematicians can show, using a Taylor expansion, that the error, so the difference between the exact solution and the numerical solution for this method is a linear function of delta t, so of the step size. There we need some assumption on the differentiability of the model function f, but in our case, in the cases that we have, both for the energy balance model and the predator-prey model, these functions are differentiable, so this usually holds. And this notation here with the big O is or means that there's a constant in front of this delta t, and this constant in general depends on the derivatives of f and also on the time. So if you compute on a very long time interval, the capital T, so the length of the time interval, or the difference capital T minus T0, it will also affect the constant here, which is natural. If we perform this computation, we make an error in every step, and this error accumulates because we proceed in time. And the error we made in the first step, we will not get rid of. It will be propagated throughout the computation. But nevertheless, this is true. So in exact arithmetic, we can expect that the error goes down if delta t goes down, and that's a linear dependency. So the idea is, if this is the time, I want to compute from time step tk to tk plus 1, where this is the step size delta t, and I have here my unknown solution y of t. This point I already have, and now I want to approximate this point here, which is unknown. And what I take with the explicit Euler method, I take the slope of the function at this point, at the point tk, which now points in this direction. This is the slope, so this is y dot of tk, which is given by the differential equation as f of yk tk. And I take this slope times the step size delta t, so I approximate yk plus 1 as yk plus delta t f of yk tk plus 1, and I will end up at this point here, which is only a rough approximation in this example. There is also another interpretation of time integrators which helps to construct or to understand different time integrators, because we can also, on the last slide we approximated the time derivative directly. We can also use the fundamental theorem of differential integral calculations, or of calculus in English, the fundamental theorem of calculus, that we integrate this ODE, which means then so if we integrate the ODE from tk to tk plus 1 on our time grid, we get that the difference of the two values of the function is equal this integral over the derivative. And since we know what the derivative is, we can also approximate the difference of two of these function values at these two time instants by the integral over the model function. And now, since we don't know y here on the right hand side, but we can approximate this interval, and a very easy way to approximate this interval is by just taking the interval length times a point in the interval. And if we take the leftmost point of the function f, then we get f of yk tk, and then the length of the time interval is delta t, and we get this approximation. And now putting these red things and the blue thing together and setting again yk for the approximate solution at the point tk, we again obtain Euler method. So what I want to do is I want to integrate my function f here between 2 points tk and tk plus 1. So in fact this is the function f of y of t, so the mapping t maps to this function. I want to integrate this, so what I want to do is I want to approximate this area here, and what I now can do is I can approximate this by taking this value, which is f of yk tk, times this length here, which is delta t. So I approximate the interval by this red area, and the red area is delta t times f of yk tk. So an alternative time integrator that we have is the so-called improved explicit Euler method, where we do, in formulas, we do the following thing. We first compute one intermediate step performing with Euler method but half step size. We compute some intermediate value. I call it here yk plus 1/2 because it corresponds to the point between tk and tk plus 1. And now I use the value of my model function at this new time point, or at this new point, intermediate point that I generated, and I take the slope of y, or the value of f at this point, to make the full step. I will show you a graphical representation, and what we get, we can do this, and we get time integrator, which can of course also be written in one line. Then it looks like the blue thing here, and we can see that it's a more complicated thing, because now we don't have just f of yk tk here, we have some more involved thing, and in the general form this is written as the general form of a one-step method, where we have the blue thing is called the increment function. It's a function phi. It depends on f, of course, on the model function. It depends on the last point of the solution. It depends on the time point, and it depends on the time step. But it only takes the last point for y and t to compute the next yk plus 1. That's the reason why it's called a one-step method. And there's a variety of these kind of methods which construct increment functions phi, which are similar to this one or even lengthier, to get a better approximation. Because with this method it can be shown, also by Taylor expansion, that this is a second order method, which means, again under some assumptions on the differentiability of f, the difference between exact solution and approximate solution is now a quadratic function of delta t. So there's again a constant depending on the derivatives of f and on the length of the time interval, but delta t square is the term which describes the error. So if we here use smaller time steps, the error becomes even smaller. So this is called a higher order, or more exactly a second order method. As above, I want to approximate the integral of this function, and now the idea is I just take the point here in between, take the corresponding function value and approximate the integral by this rectangle. So I need the function value at this point, and take again then delta t times the function value at this point, which would be y of tk plus delta t half at the time tk plus delta t half. But since I don't have this value here, I have to approximate this by one step of the Euler method with half step size. And the second value is the same as above. With the improved Euler method, I will do only a step of half step length from tk with this slope. So I go to this point. Now, through this point, there is another solution which is may be looking something like this. Now at this point, at tk plus delta t half, I take the slope of the parallel solution of the red one here, which is something like this. And now shifting this slope, I take this slope and I shift this and go from the original point tk with this new slope the full step here. And I end up with an approximation which is yk plus, so this is my new yk plus 1, yk plus delta t, the slope at this intermediate point that I computed with the Euler method, and at the time step tk plus delta t half, if the function depends explicitly on t. And this can also be interpreted with the integral formulation. So again, I integrate the ODE from tk to tk plus 1. I approximate the integral, but now by the midpoint rule. So I take now the function value, I take the length of the time interval, but I take the function value of f at the midpoint of this time interval. The time interval is tk to tk plus 1, and the midpoint is tk plus delta t half. So this is now the midpoint. And from integration, from numerical integration in numerical mathematics, it's known that this is a better approximation. But since the value ytk plus delta t2 is not given, this is what I called on the last slides yk plus 1 half, we have to approximate it. And we can approximate it by an Euler step. So we approximate this ytk plus delta t half by performing an Euler step with half of the step size. And again, we obtain the improved Euler method. And with this idea, people constructed many of these kind of methods. The general form is called a Runge-Kutta method, an explicit Runge-Kutta method. Remember, this is all explicit because yk plus 1 is only at this side of the equation. We don't have to solve any kind of implicit equation. We can just insert yk and delta t and whatever we have to obtain yk plus 1. Now I come to the point of the modularization of climate models and of simulation models in general. For climate models, you will find that many climate models have the following basic structure. Operational and real-world climate models usually have some initialization. They read a lot of data, so maybe description of the Earth's surface, the topography, and also for the oceans, and maybe initial values. There usually will be something like an init model. And then the second part will be the actual run, so the time loop. And This, of course, uses a time integrator, and the time integrator itself uses or needs the model function f if there is a model function like in our examples. And at the end, there is often something like a finalized model where maybe things are stored. So this basic structure can be seen in many climate models. And it's a good idea to, if a climate model really needs an initialization, reading data, and a finalization, writing data, then it makes sense to, on a very coarse level, to structure a climate model code like this. The aims of the modularization is flexibility. And one point, flexibility means with respect to the climate model, or here the ODE. It shall be possible to integrate an arbitrary ODE system of arbitrary dimension. We already had it now 2 examples. The energy balance model is just 1-dimensional. The predator-prey is 2-dimensional. Moreover, the time interval, the initial values, they should be arbitrary. And we have to take into account that climate models, they have parameters inside. Especially for this predator-prey models, we want to play with this alpha, beta, gamma, delta, lambda, mu, and we do not want to rewrite the code or to have hard-coded constants in the code. We want to easily change these parameters. On the other hand, we want to have flexibility with respect to the time integration method. We have now already 2, and as I said, there's a variety of methods that can be found. And we want to compare them, or if the accuracy of one method is too low for us, if Euler method is needs 2 small time steps, we might to switch to the improved Euler method where the accuracy is better. And of course we will also adjust the step size so that we can compare. Maybe Euler method with a smaller step size is better than improved Euler with bigger. We can compare, we can assess the quality of this method, because we have also to think with this method a time step. Even if we can make bigger time steps, we have to think about the cost of one time step. And if we compare Euler to improved Euler, then you can see Euler method just takes 1 function evaluation in every time step, whereas the improved Euler method takes 2 function evaluations in every time step. So it's always to look what is better, taking a higher order method, which usually involves more function evaluations in one step, or you use a lower order method, which uses maybe less function evaluations but needs a smaller step size. So this has to be taken into account. Yeah, and our examples are here energy balance and predator-prey model, explicit Euler and improved Euler, and of course different initial values, parameters, time intervals, step sizes. So that's a motivation for modularization. And if we now come to the realization, there are 2 ideas and 2 paradigms of programming. So it's what's sometimes called structural or procedural programming, and the other is object-oriented programming. So in the structural programming, there's a strict separation of data and functionality, functionality meaning operations, functions, or subroutines, or whatever they are called. So the idea is the functions operate on the data. There are clearly defined interfaces or signatures, so there is something like, if I have real variable x and y, then the function do something, operates on the real variable x, on the parameter x, and returns a y which is also real. So this is clearly defined for every function. And then I use it just like this, y do something of x. In the object-oriented setting or paradigm, the data and functionality are combined in classes. So the functions they're called member functions or methods. They are defined inside the class. They also have a clear interface, but the idea is they are connected to the class because they are defined inside. And the usage is then from the notation in many languages a little bit different with this dot notation, which sometimes is referred to the methods sends a signal to the object. So in the syntax, of course, this depends on the language, how the syntax of the language is. And this is just a dummy language, this is not an actual language that I used here. It's just for instruction. That's the way it looks like. And the main difference is here in this line and in this line, and where the definition of the function or method is located in the code. And it's difficult to say what is better. So usually object-oriented programming is regarded as the more advanced paradigm or method. But in very complex codes like climate models, you will nearly find no object orientation. So the idea here is not to say the one is good or one is bad. The idea here in this lecture is try out what you are used to. Some of you might not know object-oriented programming. Some other might be very used to it. Maybe it's a natural way for you to think object-oriented, so you can do both. In the structural programming setting, the main focus is on what kind of functions do we need. So we have functions for time integrators and we have functions for the climate model. And so we would have for the time integrators now have to write a function Euler, improved Euler. And for the interface or the signature, what are the necessary parameters and what do these functions return, or what do they have to return to be usable? And the similar thing is for the climate models, or the right-hand side F of the ODE or the model function. We need to have then a function energy balance model and another one predator-prey. And again, what are the necessary parameters? What do these functions return, and where and how will these functions be used? They have to be used in this time integrator. So one question is, how are these functions passed to the time integrator? And where and how are model parameters set? Because the functions have model parameters, at least the predator-prey has model parameters. And how can they be passed to the model function if the outer function is a time integrator? Because the time integrator operates on the model function, but from outside I might want to change the parameters. And then where are parameters like the time interval set? And is there a main function that gets the model function and the time integrator function as parameters? So there's something to think about how this can be realized, that it becomes usable. And if you do this as an exercise, you should always think there might be even more models, not just two, and also not just two time integrators. So it should be somehow general. That's the idea of flexibility. In the object-oriented setting, again, the idea is now to combine the data and the operations to classes. And the motivation for this in object-oriented was that operations depend on the data that are applied on. For example, multiplication would be a very simple standard example. Multiplication means different things for real complex vectors, matrices. And so a multiplication operator or function would be different in every class if I write a class for vectors or for matrices, for example. One advantage which can be useful in our examples here is the inheritance. So it's possible to define common data and functionality in a superclass and then allow a specification or specialization extension in subclasses, which is called inheritance. And the subclass inherits all the properties, so the data and the functionality from the superclass. And because we have several model functions, and we can think about what do they have in common, and we also have several time integrators. What do they have in common? We can also ask, and we can find something. And an additional feature in object-oriented programming, which is regarded as an advantage, is the access control for data and functionality. So I can, if I write a class, I can clearly define some functions or member functions should be used or can be used by the user of this class, and some others can only be internally used. The Unified Modeling Language, UML, is a visual language to describe relations between classes. And this is what I show here in the last part of the lecture. So this is, for people who are familiar with object-oriented programming, you will know this, but I will describe a little bit the concept here, how inheritance could be used. So in UML, in this Unified Modeling Language, there are class diagrams which can be used to describe the relations between class, so inheritance relation. And this arrow here means that this derived class is derived from this superclass. So this is a subclass, or children or child class, and this is the parent class. And in this object, in this UML, usually here we have the name of the class, and then we have here the data, and we have here the methods. And here's also used plus or minus, is always used as indicator for public or private. So private means this can only be used inside the class. So if I have here private data which has some name and a data type in the programming language, then it can only be used inside the methods of the class. Public is public to the outside. So if somebody builds an object of this class, creates an object of this class, everybody can use the public data, and the same is for the method. Important. Climate this is for us is not the main general thing. Now the plus and minus, also time integrated complete here. So this is a notation where you can find here always for the data you differ in accuracy and effort, of course, and for a method you see name somehow the parameter type and the type of the return value. Time integrators can be motivated by integrating the ODE and then approximating the integral, which gives an idea above in this superclass. It's different. In this case, it's time integrated. Even an abstract complexity. An abstract class means this is just some template flexible some data and it's useful for both, for time integration and for different models. But I cannot build an object or create an object of this class itself. It's more like an abstract concept. In the object-oriented setting, this is called hierarchical class, and that's the reason why this is in the structure of the code. But this is the basic can be useful in inheritance. So the derived class has all the data and the methods from the superclass and extends it. That is also the keyword that it used. Yeah, how can we use this? We can use this in something which is also called a semi-discrete pattern, so referring to design patterns. If you are familiar with this concept of design patterns, then yeah, that might ring a bell in your brain, but it's not the main important thing. The main important thing is here now that I build a superclass for all models that I want to integrate that are integrable. And my model then is just a subclass. And this is an idea here where some methods are defined, and the main point here is we have an integrate method. So this model can integrate, perform one integration step. And there are also some other methods here defined, maybe an assign method, a multiply method, an addition method, where two models can be added, where a model can be multiplied by a real number, and there is an assign is possible. And there is a method which is here called dt, which takes an integrable model and returns an integrable model. And this refers, if you think at what happens in a one-step method, you take let's say use the Euler method, we have yk plus delta tf of yk. And so we need something like a multiplication by a real number, the real number being the time step. And the f is the thing that is represented by what's here called d dt. It's the right-hand side of the differential equation. So this is a concept which can be used for a general abstract class where all models fit in. So because every model that should be integrated needs at least some of this functionality, and then every model is just can be just a subclass. Similar thing holds true for the time integrator, and this is what's called a strategy pattern, again referring to design patterns, but that is not the most important point how this is called, because it's a time integration strategy. And the time integrator has a method which is integrate, which performs a time integration, and it has a parameter or data which is a time step, and the explicit Euler is then one realization of this general template or abstract class in object-oriented programming. Explicit Euler is then one subclass, and the improved Euler can be another one. So this would be a simple concept for semi-discrete and strategy pattern for a class hierarchy. This is just a suggestion. This is taken from some literature, and you can try to realize your modularized version of the climate model and the time integrators following this idea here, but you can also do it a little bit differently. But the basic structure is that we have two abstract classes. One is for the model and one is for the time integrator, and then the explicit Euler and the improved Euler method are just subclasses, and the predator-prey and also the energy balance model is just a subclass. Is important in this lecture. So climate models have the same general structure. Also time integrators have a similar or common structure. Time integrators have a different accuracy and effort. And the time integrators can also be motivated by integrating the ODE and then approximating the integral. So this is a different way to motivate different type of time integrators like Euler or improved Euler. So a flexible software framework can be useful because we have different climate models and we have different time integrators. So it can be useful for time integration of different models. And it can be realized in a structure or in an object-oriented setting. And the features of inheritance, which is a part of object orientation, allows a hierarchical software design, which can be used in this example.